In this video, we will learn how to derive demand function for good x given the utility function and the budget constraint. The question is, given the utility function is utility is equal to x raised power 1 upon 4 times y raised power 1 upon 2, x and 2 are the two goods, and budget constraint is price of x times units of good x plus price of y times units of good y should be equal to total income. We have to derive the demand function for good x. Options are being given. We need to find out the correct option. Okay, so what we are being given here, we are being given this utility function. Our endeavor is to maximize the utility, that is u is equal to x raised power 1 upon 4 times y raised power 1 upon 2. We want to maximize this utility function subject to the budget constraint, that is price of x times units of good x plus price of y times units of good y, and it should be equal to the total income. Okay, so graphically what exactly is meant by this? Rather, let us first find out the optimal condition here. Okay, so first order condition for maximization requires that the marginal rate of substitution between good x and y should be equal to the ratio of the prices, that is price of x upon price of y. Okay, MRS is simply means the slope of the indifference curve, and this px upon py means the slope of budget line. Okay, slope of budget line. Okay, graphically what exactly is meant by this? So we need to find out the optimal bundle, that is the demand function for good x, that is, let us say we have x on the horizontal axis, y on the vertical axis. Okay, we have this marginal rate of substitution, that is, we need to draw the, let us first draw the budget constraint. Let us say this is our budget constraint. Given this budget constraint, okay, given this budget line, consumer wants us to reach to the highest possible indifference curve. Okay, so highest possible indifference, let us say this is indifference curve 1. Okay, IC1, and let us say this is indifference curve second, let us say IC2. Okay, so with the given budget, consumer wants us to reach to the highest possible utility level, and the highest possible utility will occur at a point where the slope of this red line, which is the budget constraint, and the slope of indifference curve are equal. It occurs where these two are tangent with each other. Okay, so at this point, okay, this point exactly depicts the, it is a point where MRS is equal to the price ratio. Okay, that means at this point slope of this indifference curve and slope of this budget line are equal. Okay, now MRS is simply equal to the marginal utility of good x upon marginal utility of good y, and it should be equal to price of x upon price of y. Now what is marginal utility of good x? Marginal utility of good x, let's first calculate. Marginal utility of good x is simply the partial derivative of utility function with respect to good x. Given this utility function, we need to, differentiate this with respect to good x. So derivative of x raised power 1 upon 4 will be equal to 1 upon 4 will become coefficient by power function rule. Then we have x, and this, the exponent of x will be subtracted by 1, that is 1 upon 4 minus 1. So we have 1 upon 4 minus 1, it becomes minus 3 upon 4. So here we will have minus 3 upon 4, and y raised power 1 upon 2 will remain same because we are taking the partials here. Symmetrically, we need to find out the marginal utility of good y, and it is simply the partial derivative of utility function with respect to good y. So again, this with this utility function, we need to partially differentiate, this time with respect to y. So the rather the exponent of this y will become coefficient. So we will have 1 upon 2, x raised power 1 upon 4 will remain same because we are taking partials with respect to y, and the exponent of y will get subtracted by 1, that is 1 upon 2 minus 1, it comes out to be minus 1 upon 2. Okay, simple thing, we are using the power function rule here. Now mux upon muy means this, Okay, so mux, in place of mux I have 1 upon 4 x raised power minus 3 upon 4 y raised power 1 upon 2 divided by marginal utility of good y, we calculated it as 1 upon 2 x raised power 1 upon 4 times y raised power minus 1 upon 2. It should be equal to the ratio of the prices of good x and y. Okay, let us solve this now. So we have 1 upon 4. I can write 1 upon 4. Transposing this to numerator, it will get multiplied and reciprocated. It becomes 2 upon 1. Here we can do one thing. Let us transpose this y raised power minus 1 upon 2 to numerator. Okay, if I transpose it to the numerator, what will happen? Let us see. So we have y raised power 1 upon 2. Transposing this, it will get multiplied and exponent sign will change from minus to plus. So it becomes 1 upon 2. Similarly, here we have x raised power 1 upon 4. Now this time we transpose the numerator to denominator. It will get multiplied but exponent sign will change from minus to plus. It becomes 3 raised power 4. It should be equal to price of x upon price of y. So what will we get? So this is 1 upon 2, 1 upon 2. Bases are same, we can add up the exponents. It becomes y divided by here x raised power 1 upon 4 times y raised power 3 upon 4. 1 upon 4 plus 3 upon 4 sums up to 1. So we get here x. It should be equal to price of x upon price of y. Let us solve for y here. So y will be equal to price of x times price of y. Transposing this x and transposing this, it will get multiplied. Okay. Now to calculate the demand function for good x, what will we do? We simply plug this y is equal to this stuff into the budget constraint. Okay. So for this, let me rub this out. I don't have the space here. So plugging this y here, what will we get? And let us see here. We will get, we have price of x times units of good x plus price of y times units of good y. For y we calculated this, that is twice price of x times, divided by price of y times x should be equal to the income. Okay, so here this py and py gets cancelled. We are left with price of x times x. Then we have plus twice price of x times x should be equal to m. So since these are the like terms, we can add them up. So we have so px into x plus twice px into x, it becomes 3 times px into x should be equal to m. Solving for m, so x will be equal to, transposing this term, it will get divided, so we get m divided by 3 px. This is the demand function for good x. So the correct option should be, okay, so we don't, I hope I have done the calculation correctly. I don't see any 3px in the denominator, so I guess the options are incorrect. Let us, and I am I guess I am sure that I have done it correctly. So let us manipulate the options here. So we have 3 times px. Okay, make sure you also check this out whether I have done it correctly or not. So this is the demand function for good x. Similarly, we can calculate the demand function for good y. Simply plug x is equal to this stuff here in this function. Okay, we will get the demand for good y. And let me calculate it here. So y will be equal to twice px divided by py times this m, so rather the value of x which we got here, m divided by 3 px. Okay, so here px and px will get cancelled, so y will be equal to twice m divided by 3 py. Okay, so this is the optimal bundle for good y, or demand function for good y. I hope I make myself clear in this video. Thank you.